So this is the definition of the cross product. If I've got two vectors, and by the way, the vectors have to be length 3. They have to be 3-dimensional vectors. If I've got two vectors, I'm going to call, the first one is going to be vector u, and whenever I do the little subscript, that's going to tell me which entry in the vector I'm talking about, u1, u2, u3. And then this is the formula. If I say u cross v, then this is the resulting vector. That's a lot. Make sure you write this down and make sure you write it down accurately, but it's a lot to memorize. I'll tell you a little trick I have for memorizing this. And to give you a little bit of background for this trick, I was born in 94. I was born in 1994. And when I was like 5 or 6 years old, the number one game at the time was for the Nintendo 64. It was called Legend of Zelda: Ocarina of Time. And if you haven't ever played it, you should really play it. I mean, it might not actually hit the same for this generation because you guys are used to like really good graphics. And the graphics are very rudimentary when you go back and play an old Nintendo 64 game. But even today, I think it's still like the top of the list on like Metacritic, you know, the website where they get together professional video game critics and they compile their scores. And so when you're playing the first level in Ocarina of Time, you come across this guy and he gives you the trick to solving a puzzle later in the game, because this is part combat, part puzzle game. And so he gives you the answer to a puzzle, and this is what lives in my brain, right? He says the order is 2, 3, 1. Now remember that, okay? The order is 2, 3, 1. This is important. So what we're going to do to memorize the cross product formula is this. We're going to say u cross v is equal to a vector that has 3 entries. And every single entry in this vector is going to look like this. It's going to look like uv minus uv, uv minus uv, uv minus uv. Okay? Just write that down. Hopefully you can remember that part. Okay. This is the part where you go home, you play Ocarina of Time, you learn the order is 2, 3, 1. All right? See the subscripts? 2, 3, 1. Now what comes next is this. In the first entry of this product, since it's the first entry, the subscript 1 is never going to appear. Instead, it's going to be 2, 3, because I'm trying to avoid the number 1. And then, because I don't want to subtract the same thing, I'm not going to subtract 2, 3 again. I'm going to subtract 3, 2. Okay? Okay, next entry. It's the second entry, so I'm going to avoid the subscript 2. Instead, I'm going to write 3, 1, and then I've got to reverse the order 1, 3. Okay? And then last entry, I can't use the number 3, so I got to use 1, 2, and then reverse it 2, 1. That's how I remember the cross product formula. And you can too. Okay. So this is one of those crazy things, you know, I think it was Carter asked a good question last time. He was like, why is the dot product of two vectors a scalar, right? And the answer was, we just do that because it's useful, right? We only defined this as a method of multiplication because it's useful. The story is the same for the cross product. You might ask, why do we care about this really, really weird formula for how to calculate the entries of a vector? And the answer is, we only care because it's useful. And I'll show you why it's useful here in a minute. But first we practice. Here is an exercise I might give you on a test. It just says calculate the cross product of the following vectors. And so u cross v is, and then if I were taking a test and I didn't want to make any little mistakes, I would go ahead and rewrite the whole thing from scratch. So be very careful. And I think 2, 3, 1. And then I think 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. Okay. Now we've memorized the formula. What is U2? 5. What is V3? 2. So 5 times 2 is 10. What is U3? What is V2? Okay. Anything times 0 is 0. What is U3 times V1? Negative 6. What is U1 times V3? Okay. What is U1 times V2? And what is U2 times V1? Ta-da. So the cross product is itself a three-dimensional vector. The dot product is a scalar, but the cross product is a three-dimensional vector. Okay, so we feel good about how to do it? Okay. So the cross product has the following properties. The cross product is not commutative. That means the order in which you multiply two vectors really does matter. But it also has a weird property. It's the anti-commutative property. That means if I were to switch the order that I'm taking a cross product, then I'm just going to get a negative sign or a minus sign in front of each entry. The cross product does have the distributive property, just like multiplication, just like the dot product. And it does have the associative property, which is just like ordinary multiplication, just like the dot product does. So the only weird thing about the cross product is this anti-commutative property. Cool. Next, we're going to do a bunch of proofs stuff. This says, if I take a vector and I cross product with itself, then it has to be 0. Okay? That's what I'm trying to prove. Now, if you want to prove this, then it's really easy. You're just going to use the formula. Because if I do u cross v, then obviously it's like uv minus uv and uv minus uv and everything. But if I do a vector cross product with itself, let's see what happens. Okay, 2, 3, 1. And then remember 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. Do you see what happens? Every entry is going to be 0. So whenever I write u cross u equals 0, what I really mean is that this is the 0 vector. This is a vector that has 3 0 entries. All good? So the next interesting property of the cross product is this. If I have u dot v, which is a scalar, squared, plus the norm of u cross v, And u cross v is a three-dimensional vector. But when I take the norm of that vector, the norm is a scalar squared, and I add those together, then I get the norm of u squared plus the norm, or times the norm of v squared. I think this is interesting. To me, this kind of, well, maybe we'll come back to this. I'll tell you why this is interesting to me in a minute. But first, let's prove this. And to prove this, we are just going to use the dot product and cross product formulas and the norm formulas, right? But basically just use the formulas, expand it, and then you'll see that the left side is equal to the right side. So when I've got u dot v, that's going to be u1 v1 plus u2 v2 plus u3 v3. That's how I take a dot product. And then we want to square that, right? Plus the norm of u cross v squared. So the norm is what I get whenever I do the square root of each entry squared added up together. You guys remember the norm? And these entries look like uv minus uv, uv minus uv, and uv minus uv. Remember 2, 3, 1, 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. Squared, that's the norm squared. And then the norm of u would be u1 squared plus u2 squared plus u3 squared times the norm of v, which is v1 squared plus v2 squared plus v3 squared. Okay. So one thing we can do right away is the square roots, right? If I'm taking the square root to get the norm and then I square it, then these cancel each other out. And instead I get something like this. I don't even need those parentheses. It's a little extra. And what follows is going to be a really obnoxious amount of algebra. Just basic, when you square this, you've got to distribute everything properly. You've got to do u1 squared v1 squared, and then u1 u2 v1 v2, and then u1 u3 v1 v3, and then you've got to handle all the combinations like you normally would if you're being super careful with your algebra. And at the end of expanding everything out, you'll find that the left side of this equation is equal to the right side of this equation. I'm not going to do that.
Why not?
Because, you already understand what the process is, right? It's just going to take too long. Okay. I'm glad you know. But that's what it would look like. So that's an important formula for talking about something like this. This statement is u cross v equals 0 if and only if u and v are parallel. So that means if u and v are parallel, that implies that u cross v is equal to 0. And that also means that if u cross v is equal to 0, that implies that u and v are parallel. That's what we're saying right here. If I want to prove this, then we start by saying, remember how u dot v squared plus the norm of u cross v squared equals norm of u squared norm of v squared? Well, what is u dot v? U dot v is the norm of u times the norm of v times cosine of theta, where theta is the angle between the vectors. This is what we learned last week. So we're borrowing that from last time. And so here, when I have u dot v squared, we're talking about norm of u squared, norm of v squared, times cosine squared of theta, plus this cross product, norm squared, and that's supposed to be equal to norm of u, norm of v squared. Okay. So if u and v are parallel, what does that mean about theta? Parallel vectors have what theta?
0.
Yes, the angle between parallel vectors is 0. So parallel vectors means theta is 0. And then cosine of 0 is what? 1. And that means cosine squared of 0 is 1 squared, so it's 1. And then I don't have to worry about that. And so now my equation looks like u norm squared times v norm squared plus something equals u norm squared plus v norm squared. So that means u cross v norm squared has to be 0 for that equation to be true. So that means u cross v norm squared must be 0. And if the norm is 0, that means the vector has to be the 0 vector. Because if a vector is anything besides 0, 0, 0, its norm is not going to be 0. So now we just showed that if you have parallel vectors, then their cross product is 0, 0, 0. The cross product of parallel vectors is 0, 0, 0. What about the other direction? The other direction of this proof says, if the cross product is 0, that should imply that I have parallel vectors. And so go back again to this equation right here. I'm going to circle it for you. If this cross product is 0, then obviously its norm is 0 and this term is 0. And then my equation is going to be norm of u squared times norm of v squared times cosine squared of theta is equal to norm of u squared times norm of v squared. And that means cosine squared of theta has to be 1. And if cosine squared of theta has to be 1, that means theta has to be 0. Theta 0 means the vectors are parallel. Okay? Does everybody follow that? Cool. All right, what about this? The vector u cross v is orthogonal to both u and v. Who can tell me what the word orthogonal means?
It's basically like perpendicular, but for 3D, in 3 dimensions or more, however many dimensions.
Yes, it's a good way to generalize the idea of perpendicular. What's like the math definition? If I say that the vectors a and b are orthogonal to each other, that means...
Is it the dot product equals 0?
Yes, great. That means the dot product is equal to 0. So if I say a and b are orthogonal, we defined the word orthogonal to mean a dot b is equal to 0. If two vectors are orthogonal to each other, their dot product is 0. So how do I go ahead and prove this theorem? I would check to see if u cross v dot u is equal to 0. And if u cross v dot u is equal to 0, that means the cross product is at least orthogonal to u. And so here is u cross v. I'm writing this formula down a lot of times so that, again, hopefully it helps you stick in your brain, because this is one of the things you got to memorize here. 2, 3, 1, and then 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. And then we're taking the dot product of this with u, which is u1, u2, u3. And this is going to be an obnoxious thing to write out, but I'm going to try u1, u2, v3 minus u1, u3, v2 plus u2, u3, v1 minus u1, u2, v3 plus u1, u3, v2 minus u2, u3, v1. And we'll see what that's equal to. Now, we're trying to simplify, right? So I see a positive u1, u2, v3. I see a negative u1, u2, v3. Those cancel. Then I see a negative u1, u3, v2, and I see a positive u1, u3, v2. Those cancel. And then last, I see this u2, u3, v1, and this u2, u3, v1. Those cancel out. And so this is equal to 0. That means they're orthogonal. And you can do the same thing to double check that u cross v dot v is equal to 0. Also, if you believe in the anti-commutative property, which is if I switch the order of the cross product, I get the same vector, but with a negative sign. Well then, imagine taking v cross u dot u, v cross u dot u. I should get exactly the same vector, but with a minus sign in front. And then when I take the dot product, everything should cancel out as well. Negative 0 is still 0, and so I'm good. But this is the idea. So after I take a cross product, I've got, a three-dimensional vector u in space, another three-dimensional vector v in space, and when I take their cross product, the resulting vector is orthogonal to both of the other vectors. In other words, it's perpendicular to both of the vectors you started with. Okay? Okay. Here we go. And hopefully this looks a little bit familiar to you. But you should know this one, that sine of theta is equal to the norm of u cross v divided by norm of u, norm of v. And this should remind you of something. Do you remember last week we said cosine of theta is equal to what? The dot product over the magnitudes, or the norms. Yeah. So this is from last week. We were talking about dot product. But this is the new thing that you have to also know. Again, I know that the formula for the cross product looks crazy, and you might say, who would ever want to come up with this crazy formula? Well, we only invent it because it has some kind of usefulness to it, right? The dot product kind of evokes the cosine of the angle between the vectors, and the cross product is the complement to this idea. It's kind of like the sine of the angle between the vectors. So how would I prove this? It's a good question. Let me think. I think I would start off by saying this. This is something that we proved via brute force, right? Or at least we sketched the proof. I told you what it would take to prove this statement right here. And then what we're going to do is we're going to use this to substitute in for the dot product. And so where the dot product is, I'm going to write norm of u, norm of v, cosine theta. And of course it's squared, right? Plus the norm of u cross v squared is equal to norm of u squared, norm of v squared. Then let's divide both sides of this equation by the norm of u squared, norm of v squared. And the equation becomes cosine squared theta plus the norm of u cross v squared divided by norm of u squared, norm of v squared is equal to 1. And this should remind you of a trig identity. The trig identity goes cosine squared theta plus blank equals 1. Sine squared theta. And once again, I've got cosine squared theta plus something equals 1. That means that something right there has to be sine squared theta. And then you take the square root of both sides, and then you get the identity we're trying to find. Oops. Okay. So, you see where it's coming from? This angle identity. Now, if I wanted to find the angle between two vectors and I know what those two vectors are, which one of these is a more convenient formula to use? The dot product one, right? The dot product is fast and easy to remember. The cross product is hard to remember. It takes a lot more operations. We would use the cosine formula if we were actually trying to find the angle between vectors. But I think it's nice to know that the cross product has some kind of geometric interpretation in terms of the sine function. How about this? The norm of u cross v is the area of a parallelogram with u and v as sides. So let's talk about that. Here are my nice vectors u and v. And if I want to make a parallelogram out of this, I need to also scooch up a copy of the vector u and scooch over a copy of my vector v, like that. And now I want to find the area of this parallelogram. Do you know how to find the area of a parallelogram? Here's what we're going to do. I'm drawing what's sometimes called an altitude. And I'm also going to draw a parallel. No, that's not right. A diagonal. I don't know why I said parallel. Parallelogram, I guess. And so that diagonal splits this up into two triangles, right? What's the area of a triangle? Do you remember that one? 1/2 base times height. So the area of one triangle is going to be 1/2 base times height. And the area of the other triangle is also going to be 1/2 base times height. But these triangles have the same height, right? in the same base. So it's really just going to be base times height. The area of a parallelogram is just base times height. Okay, well, that height is it's related to that theta in the corner. For this little right triangle in the bottom left corner, sine of theta would be the opposite side over hypotenuse. Sine of theta would be h over norm of v. And that means h is equal to norm of v times sine theta. And that means my area is going to be norm of u, norm of v, sine theta. And that is equal to the norm of the cross product, right? Based on what we just saw on the previous page. So if you get any kind of weird question that's asking you about the area of a parallelogram, maybe the easiest way to find the area of the parallelogram is that you take the cross product of the vectors that make up the sides of the parallelogram and then take the norm of that cross product. So again, just to recap what we know about the cross product, you multiply two vectors that have dimension 3, right? Two three-dimensional vectors. Their cross product is another three-dimensional vector. It's orthogonal to the first two, according to the right-hand rule. So this is u and this is v, then this is u cross v. And the norm of this cross product is the area of the parallelogram that u and v make. And that means if u and v have a really small angle between u and v, the area of the parallelogram is small. And if they have a 90-degree angle between u and v, then your parallelogram is a square, and that's the maximum area you can get out of it. So the cross product is going to be largest when these vectors make a 90-degree angle with each other, and it's going to be the smallest when they make a very small angle with each other. And these are kind of the useful properties of the cross product. Later this semester, whenever we do a bunch of crazy integrating over surfaces and stuff, I'm going to remind you of all of these things and say, wow, wasn't the cross product so useful? Wasn't it so great that it's orthogonal to the first two vectors, and it has a magnitude that's depending on the sign of the angle between them, and so on. Okay, here we go. Find a unit vector that's orthogonal to both a and b. How do I do this? I take the cross product. So if I want a vector that is orthogonal to a and b, I just have to take their cross product. That gets me that nice orthogonal vector I'm looking for. And so remember, this is AB minus AB, AB minus AB, AB minus AB. And then it's 2, 3, 1, 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. A2 times B3 is 0. A3 times B2 is 2. A3 times B1 is 2. A1 times B3 is 0. A1 times B2 is 2, and A2 times B1 is negative 6. Please correct me if I make any little mistakes. I like to make a lot of mistakes when I do math problems, so please find those as soon as you can and let me know what I did wrong here. And then the other thing here in this problem, it says I need a unit vector. So not just A cross B, but I need this to have a norm of 1, and I can do this if I divide by the norm of that vector. And so the norm of A cross B is going to be the square root of negative 2 squared plus 2 squared plus 8 squared. That's 4 plus 4 plus 64, that's 72. That's the square root of 72. Square root of 72 is what, 8 times 9? So that would be 6 square root 2. Right? 2 times 4 times 9. So it's 2 times 3 times 2. Yeah, okay. And so then whenever I want to actually write down this vector, I do negative 2 divided by 6 square root 2 2 divided by 6 square root 2, 8 divided by 6 square root 2. And I know I should be trying to simplify, I guess. So it'd be like negative square root 2 over 6, positive square root 2 over 6, and then that's going to be 4 over 6 times square root of 2, so it's going to be 2/3 square root of 2. Okay, so that is a unit vector that's orthogonal to A and B.
Would the first two be over 3 then?
So for this, I just know that 2 divided by square root of 2 is square root of 2, and I leave the 6 alone. And then here, I'm thinking about 4 divided by 6, which would simplify to 2/3, and then 2 divided by square root of 2, which would be square root of 2. Yeah. Okay, questions? Take a break and ask questions. Do you have any questions? Any concerns? No? Okay. Exercise 10 on your homework says something like this. It says the vertices of a quadrilateral have the following coordinates. So it's giving me 4 coordinates in space, and it's saying, hey, if you connect all these up, we hope that these points lie in the same plane, right? If the 4 points don't lay in the same plane together, which is possible, then it would not be a quadrilateral. Quadrilaterals are flat shapes with 4 vertices. What makes a trapezoid special? What makes it different from other quadrilaterals? Yeah. 2 of the sides of a trapezoid are parallel. It doesn't have to be both pairs of opposite sides, but one pair of opposite sides has to be parallel in order for it to be a trapezoid. So, how can I test to see whether these sides are parallel to each other? Well, I can say one of these sides is going to be AB, and I should be really clear about this too. If I'm talking about a vector AB, I like to draw a little half arrow over the top that says this is a vector where the tail is at A and the tip is at B. And you can calculate this just by subtracting B minus A. So AB is going to be negative 3, 4, 1. Another side of this quadrilateral is going to be the vector BC, which is 0, negative 2, 6. Another side of this quadrilateral is going to be CD, which is 3, negative 4, negative 1. And then the last side is going to be from D back to A, which is going to be 0, 2, negative 6. A minus, we're doing A minus D. Yeah. Okay, so then I would look at opposite sides, and I'm trying to think, are they parallel? Do you remember the definition of parallel? It means that one vector is a constant multiple of another. And I'm looking at AB and CD. But these are not, actually they are, yeah, sorry. What's the constant multiple between AB and CD? Negative 1. So yeah, those opposite sides are definitely parallel to each other. Next question, is this a parallelogram? What's special about a parallelogram? It has 2 pairs of parallel sides, so both of the opposite sides are parallel. So let's test the other one. Is this BC parallel to DA? Yes. Once again, the K constant, the scalar, is negative 1. And so yes, AB is parallel to CD and BC is parallel to DA. Since it's a parallelogram, that means I could find the area of this parallelogram just by taking the cross product of these 2 vectors and then taking their norm, right? The norm of the cross product is the area of the parallelogram. Is it a rhombus? Do you know what's special about a rhombus? Yes. A rhombus is just a parallelogram where all the sides have equal length. So to test this, I might want to take the norm of AB and the norm of BC and see if they happen to be the same. And the norm of AB is going to be the square root of negative 3 squared plus 4 squared plus 1 squared. And the norm of BC is going to be 0 squared plus negative 2 squared plus 6 squared. And so that's like the square root of 26. And this is the square root of 40. So no, not a rhombus. It doesn't have all equal side lengths. Is this a rectangle? What's special about a rectangle? Yes. The angle between sides is 90 degrees in a rectangle. So I would want to test whether the angle between AB and BC is 90 degrees. And how can I test what this angle is going to be? How can I test whether it's 90 degrees or not? Perfect. If they're at 90 degree angles, they're perpendicular, that means their dot product has to be 0. So let's see. Is the dot product between the first 2 sides equal to 0? That's negative 3 times 0 plus 4 times negative 2 plus 1 times 6. Negative 2. It's not a rectangle. Is it a square? No. Because if it's a square, it has to be a rhombus and a rectangle at the same time. And that's it. It's not so bad. Do y'all feel good about that question? Yeah?
I do. Maybe another question. If it is a trapezoid, it can't be a square, right?
No, a square is a type of trapezoid.
Square's not.
Yeah, because trapezoids is just any quadrilateral where one pair of opposite sides is parallel. So like parallelogram is a type of trapezoid. Square is a type of parallelogram. Yeah. What's funny,
I'm talking about shapes because
I'm pretty sure like my first grade teacher taught me this, right? Like I don't think I've even heard about this since first grade. Because we like talked about shapes so much back in first grade. Yeah, that's not something we think about very much. What is the area of the parallelogram with u and v as sides? Somebody tell me.
The cross product.
Not just the cross product. The norm of the cross product. That's right. The cross product is a vector, but the norm of the cross product will give me the area that I need. Oh, and this is this is the end already. Okay, discuss the cross product for 2D, 4D, and 5D vectors. So right off the bat, I'll tell you this. The cross product is not defined for (4D, 5D, ... etc. Right? If your vector has a size larger than 3, then there's just not a convenient definition for the cross product that does the same stuff that we want the cross product to do. What about 2 dimensions? Because this is a more interesting question. A 2-dimensional vector can pretend to be a 3-dimensional vector. For example, if I have a vector u, and it's just a 2-dimensional vector, u1, u2, I can kind of force it to pretend to be a 3-dimensional vector like this. Right? A 2-dimensional vector just lives in the xy plane. Well, in 3-dimensional space, if I just make the third dimension 0, now I've got a vector living in the xy plane. And we can see what's going to happen when we take the cross product of these 2 vectors. Let's try it. Remember, it's going to be uv minus uv, uv minus uv, uv minus uv. Then remember, 2, 3, 1, 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. Okay, but notice u3 is equal to 0 and v3 is equal to 0. So let me go back through, and anytime I see v3, I'm going to make it into a 0. Anytime I see u3, I'm going to make it into a 0. So I'm going to get 0 minus 0, 0 minus 0, u1 v2 minus u2 v1. So think about this. My vectors I was starting with, u and v, they were just 2-dimensional vectors. They live in the xy plane. So when I take the cross product, and the cross product has to be orthogonal to u and v, then it has to only be in the z direction. in order to stay orthogonal to everything happening in the xy plane. So again, the first two entries are going to be 0. The third entry, which is in the z direction, is going to be something non-zero. And so whenever we take the cross product of a 2D vector, a lot of times we just write down the scalar. And it's not of a 2D vector, it should be of 2D vectors is a scalar. And the scalar is u1 v2 minus u2 v1.